Ado and Matt for the invitation. I've seen some great talks here, so I was really excited to be able to talk here. So I wanted to use this opportunity to talk about a problem I encountered, which is very simply stated, and as far as we could tell, pretty much unstudied. And namely, it's to minimize a particular singular value of a matrix variable. All right, so let's just. Yeah, so this is all joint work with Al Borders, who graduated recently and is now at Uber in Pittsburgh. So I'll talk about the main thing we're trying to solve, though you already pretty much know it. Minimize a particular singular value of a matrix. Sorry. We'll talk about basically upper bounds and lower bounds. So for upper bounds, we're going to talk about some convex heuristics, and we'll see. Well, you can see if you find it counterintuitive, but most people found it pretty counterintuitive result on which is best for this problem. And then we'll talk about lower bounds, which in general were a lot harder, and some ways to formulate the problem to be able to get some lower bounds on this as well. So that's basically it. Upper bounds and lower bounds. Okay, so of course this is only a convex problem if we're talking about the first singular value. That's not what we're interested in here. Since Radu taught me that most induced norms actually are hard, I should say it's convex and you can write it as an SDP. There's some literature on dealing with the smallest singular value. For instance, I think Gu's method is probably the most popular. So there's a little bit on that, but as far as we could tell, nothing on dealing with one in the middle. And there's some recent work on characterizing the distribution of singular values for random matrices, and perhaps that'll come into play for future result. But as far as trying to have a deterministic problem and trying to optimize it, that we haven't seen. Yes. No. Okay, so just one slide of motivation so you know why I care about this and how we got here. If you don't care about control theory, it'll just be the one slide, and then we'll distill that problem of minimizing the singular value. So I do a lot of work in decentralized control, and the question we're trying to answer is to try to find some way of measuring how close are you to losing controllability. All right, so there's lots of nice binary results showing is it controllable or is it not, but as far as trying to get a non-binary measure, and it turned out there was some nice work on this in '88 that had pretty much sat there, and you can probably see why. It leads to a very difficult optimization problem. So is this here we go. So you've got lambda, which can be any complex value. There's this other difficulty we won't talk about where this set I could vary over a power set. So there are 2 to the n u possibilities there. And for each of those 2 to the n possibilities, you then have to try to minimize sigma nx, which is the size of the state. So basically this would be nx plus the number of things you can control. So it'd be the size of the state plus the number of things you can control. And the singular value you care about is just the size of A, the size of the state. And so if that can be driven to 0, that means you don't have this kind of decentralized controllability. And if it's not 0, then it gives you a measure of how far are you from losing that controllability. And that is what led us to trying to find some literature on that and coming up empty and then leading to the work I'd like to talk about. And so if you have taken some control, this will look a little bit like a PBH test. So this is indeed a generalization of that for decentralized and for non-binary. And it's maybe a little bit interesting that if you do try to do this for the centralized case, then you end up basically dealing with this and this separately, which is a minimum singular value problem. So then you can at least use some of the stuff I alluded to. But for decentralized, then you need to minimize one that's right in the middle. Okay, so let's first talk about some convex heuristics for this. And now let's state the problem that we're going to be dealing with, and it'll just be like this. We're going to minimize some sigma k of our matrix variable x. So x can be in our m by n. I'll use square examples when we do some numerical examples, but in general, it doesn't have to be square. So we're trying to minimize sigma k, and just subject to some convex constraints. So we'll assume C is some non-problematic convex constraint. So we're basically trying to figure out how to deal with this. All right, so one convex heuristic. So the first thing most people would suggest here would be this chi-fan norm, which is to sum up the singular values up to k. So if you're interested in sigma 2, all right, sigma 1 plus sigma 2, that's convex. All right, now the first thing we tried was the nuclear norm, just because A, we hadn't thought of that right away, and B, it was important if this thing goes to 0. And of course, that dropping rank, what's the most common heuristic for that? Nuclear norm. So it happened to be the first thing we tried, and it turned out it was working better than this. And I assumed for a while there was a mistake until Alborz convinced me there wasn't. Because basically, suppose it's sigma 2 that we care about. Right, if your choices are minimizing sigma 1 and sigma 2, or sigma 1 and sigma 2 and, let's say, sigma 3 and sigma 4, right, the first one would seem like the obvious choice, right? You're adding less of the stuff you don't actually want. So it seemed like that had to be better, and there had to be a mistake. But it turns out that the way they're tied together, that's not quite the case. So let me just give a toy example to try to help convince you that that there is more to it, that you do want to add some extra terms, perhaps. Okay, so suppose we are trying to minimize sigma 2, and we have two feasible points. One leads to singular values of 12 and 8, and one leads to 10 and 10, or just under 10 and 10. All right, so if you're minimizing sigma 1 plus sigma 2, right, perhaps the most intuitive heuristic, it's going to be pretty indifferent between these two, and it's going to slightly prefer the first one because it's looking at that sum. And you'd want to have the second one because this is sigma 2 is what you care about, and that's where you would get the 8. All right, but now if you bring in sigma 3, right, sigma 3 can't be any bigger than this. So that's automatically going to bias you in the way you want towards the one with the lower sigma 2. All right, so for example, right, this sigma 3 can't be any bigger than that. So you bring in, let's say, 7.9, whereas this one could go all the way up to 9.9. So then then that would bring you back to the one you prefer. And more generally, you can see how they will be tied together in this way where it might make sense to add a little bit more. All right, so I think that once we realize that, it raised the question of, okay, so it does make sense to go a little bit further, but probably not all the way to the nuclear norm. So how far do you want to go? So we'll introduce a family of heuristics, which are basically let's just look at an example. It's the easiest way. So suppose we're going to look at the 2.3, let's call it the 2.3 chi-fan norm. All right, that'll be sigma 1 plus sigma 2 plus 0.3 of sigma 3. All right, so that's convex, and that way we can define these chi-fan norms as a continuous parameter, all the way from the 2 norm up through the nuclear norm. All right, and it's convex for any of them. Okay, so we'll do some simulations here. So we randomly generate. So each index will either be fixed at a value b, or it'll have some lower and upper bounds, just to make sure this thing will be bounded. All right, so we randomly with probability 0.7 say it's fixed. The probability 0.3, it's got some bounds, and then these three things are all just uniformly generated from -5 to 5. All right, we do that 200 times. We make 200 random problems. All right, and then for each one, right, where we want to minimize sigma k, for each one we instead minimize this, this convex heuristic for all the different parameters L to see how we do. Okay? And then we'll report on the singular value we actually care about for the solution to the convex problem to see how good of a heuristic it seems to be. All right, so just show 3 or 4 examples of this. So here we want to minimize sigma 4. All right, so the black line is what we want to minimize. So we've generated these 200 problems. All right, and let's just look at the blue is the average performance, the average value of the singular value we actually care about for the different heuristics. So as you sum up to sigma 4, and here's what you get with the nuclear norm, and so on. And so we see that it does pay to go a little bit past the thing that we're trying to minimize, and here you'd want to go to maybe about 4.5 where the average dips before it starts coming up. And going to the left is just kind of a sanity check, right? If you care about sigma 4, you wouldn't want to sum sigma 1 up through sigma 3. And so indeed, we see it rise steeply that way, though it's still, it doesn't just suddenly, there's no discontinuity or anything, right? It's still better to sum to sigma 3 than to sigma 2. But okay, so I think here we're trying to minimize sigma 7, and we see we want to go up to maybe sigma 8. Trying to minimize sigma 16. We want to go a little bit past that again. So this is a pretty consistent phenomenon. And just one more thing here. So obviously you minimize this heuristic, and you don't have to stop there, right? You can use that as a starting point to then find a local optimum with some. We just used a basic subgradient method. So the blue is what you get just with the heuristic, and the red is after you fine-tune it with a subgradient method. And in general, the lesson is go out a little bit further if you're going to do that, but it usually is pretty small. But that is consistent. You can go out a little bit further if you're going to not just stop at the convex heuristic. Okay, so I mean this is all just simulations, and I really don't quite know how to analyze it. And this is one of the reasons I did want to talk about this here. Is I thought there'd be some there might be some people who would have some ideas for how to formalize this. So my kind of dream theorem would be that if you had the sigma, the singular value you're trying to minimize, and the size of the matrix, there was be a function that would tell you what's going to minimize the expectation of the sigma k for the of the solution. So it might be easier to have an actual matrix that achieves the minimum and try to recover it or something like that. But this would be the kind of thing we'd actually want. But so yeah, please talk to me if you have any ideas for how to get that. All right, so with upper bounds, pretty much everything we tried worked pretty well, and some stuff worked really well. Lower bounds were really a challenge, and it was actually probably more important for the kind of problem we're interested in, because that would give you a guarantee of how far are you from losing controllability. Yes.
So you randomly generate the problems that you were trying to solve, right?
Yeah.
Did you consider different regimes for randomly generating those problems? So I'm thinking it seems like the decay of the singular values is going to be important to this problem. Like if you were to draw a curve with the singular values going from 1 to n, right? That if it is essentially linear, it seems like you'll see different behavior than if it has a sharp growth.
If what's linear?
If just plot the singular values against n.
Okay. Yeah, which I mean, I guess would be driven by the. Yeah.
Curve if you were to plot this thing in the physics, right?
Yeah, I hadn't looked at it. I was looking more at the one you care about as you vary over the different heuristics. But yeah, that would be, perhaps I should take a look at that and flip it around to fix the problem and look over see what the solutions look like in terms of, is that what you're?
Yeah, if you somehow come up with models that are going to encourage a certain kind of behavior for those singular values within a certain range anyway, and then and to see what this looks like in those different cases, I think that could be.
All right. Well, let's talk about that later. Okay, so yeah, so lower bounds were hard. The dual function, this is the dual function. It's 0 at 0 and minus infinity everywhere else. Those are lower bounds. They're not very useful ones. There might be some possibilities I haven't looked into yet from, there's a few ways to form this as a biconvex problem. Perhaps that'll go somewhere, but for now, what we have that's actually working are a few different ways to formulate the problem as a polynomial optimization and then use sum of squares methods to derive lower bounds. All right, so of our usual setup, we're just now going to assume that that our set C can be characterized by polynomial constraints. All right, so we want to minimize sigma k subject to these constraints. So the first step is we're going to use this result that sigma k, another way to get sigma k is to look at the distance in 2 norm to the closest matrix that drops rank. All right, so sigma k is the distance to the closest rank k minus 1 matrix. All right, and now this equality, you can replace it with an inequality because looking to k minus 2, k minus 3, that's not going to help you. That's just going to make you go further. So you can make that an inequality, and once you do that, now we can replace this with w equals uv, where u and v are appropriately sized so that the product will have rank k minus 1 or less. All right, and now we're going to deal with the objective. I'm just going to first use epigraph form, all right, to put this as a constraint. You square it, and now we can use shared complement. So this is just kind of the standard trick to when you're minimizing the biggest singular value. All right, you rewrite that as an LMI. Okay, so now we have a biconvex problem. Right? The only difficulty now is the only non-convexity is w equals uv, right? Or you could plug that in here and have a problem with a bilinear matrix inequality. And that'll certainly lead to other ways to get upper bounds, but upper bounds weren't the problem. Right? Lower bounds are the problem. So lastly, to turn this into a PO, we take this the fact that this has to be positive semi-definite, and we can just write that as that has to equal some GG transpose for this extra variable g. And now we have a polynomial optimization. All right, that's exactly equivalent to the problem we're trying to solve. All right, the problem is it has a lot of constraints. Here you have m plus n squared, and here you have mn more. They're all degree 2. There are some other ways to get fewer constraints with higher degree that I won't get into. But as any of you who've played around with sum of squares knows, it blows up pretty quickly. So this wasn't tractable for all but the tiniest problems, which led to the last thing that I want to talk about, which is how to use some sampling techniques to get smaller PO, which will give you a lower bound and then a lower bound on that. But that's been working pretty well. So what we use is this Courant-Fisher theorem, which is a nice way to state singular values. So there are two different ways. So you can write sigma k in this min-max form or this max-min form. I find it a little more intuitive to think about the, wait a second. Sorry, I thought there was a box coming around here. Anyways, I find it a little more intuitive to think of the max-min form. All right, so let's just think about this for a bit before we get a little intuition behind this before we go on. So you're maximizing, so let's say we're trying to minimize sigma 2. All right, so out here you maximize over everything with dimension 2. So any plane you can take, right, you're then going to, for that given plane, all right, you're going to try to minimize the size of the output. So I don't know if, all right, so for instance, if you took the span of like V1 and V3, right, so if this was your V, you put it through there, right, then you get sigma 1 U1, right, sigma 3 U3, right, and so now when you try to minimize, right, so for normalized input, trying to minimize the size over here, right, you're going to end up choosing V3 and getting sigma 3. All right, and now you take over all these planes that you could take, you're trying to make that minimum the biggest, so you're going to end up choosing V1, V2, right, sigma 2, U2, and that's the way to make the minimum the biggest. So this ends up being achieved when this subspace you're optimizing over is just the span of the first k right singular vectors, and so then you recover the kth singular value. All right, and the other one works similarly, but counting up from the back, counting up from the last singular vector and counting back to get this in a min-max form. Sorry. Okay, so I'm just going to take this this max-min form, and the main idea that we're going to try to use is say if we have this in a max-min form, right, then if we don't get to maximize over all these things, if we just take a couple of them, right, we'll get a lower bound. It's just not as good of a maximization. So that's what we're trying to do here, and we're trying to restate this in a way where we can do that and get something computable. All right, so the first thing here is to notice that you can replace this equality with an inequality. All right, so if you let this space get bigger, right, that's not going to help you. Right, because if you let this space get bigger, then they'll just have more chances over here to make the output even smaller. So that's not going to help your maximization at all. So this doesn't change anything. And once you notice that, now you can characterize this subspace of dimension k in terms of a null space of a matrix Q. All right, so we characterize this Vk by QV equals 0. And the nice thing now is that if that, you don't have to worry about it being full rank, because if it's degenerate, well, then you just get something of higher dimension. So this formulation is nice in that way. The other way you could go here is to try to characterize it as a range space. All right, and now say we're going to have some arb, and you have to make sure that's full rank, and you could limit it to being orthonormal. And now characterize V, instead of coming from the null space of Q, is coming from the range space of R. And this actually, it's too bad I won't have time to talk about something cool happens here. In a nutshell, this subproblem is a non-convex problem that has strong duality. So that's, but what we've implemented so far is using this one. So let me show you that. last. All right, so this is just repeating what we had down here. So we can write our sigma k as the max over these matrices Q. And now the min over V, normalized V in the null space of Q. Right, that lets us optimize over all these possible subspaces in the way Courant-Fisher requires. All right, so now we have that the value of the problem we've been trying to solve. Again, just starting off with we'll square it and make it a little bit smoother. So trying to minimize the singular value squared, subject to our constraint. All right, first focus on the objective. Just put it in epigraph form. All right, adding our variable gamma. All right, now we take this constraint that sigma squared is less than or equal to gamma, and now we're going to, this is the key step where we're going to use this. All right, so if we can write this as the max over Q of this thing, now if, sorry, I should have squared this up here. So now if this is less than or equal to gamma, right, it means that the max of these is less than or equal to gamma. So it means that this has to be less than or equal to gamma for any possible value of Q. All right, so we have this now, which isn't very helpful, but we can relax this by sampling some of the Q's. Right, so in other words, we try out some of these subspaces, right, and then when we minimize over all of them here, we get a lower bound on the singular value. So that's what we'll do here is we'll replace this, that this has to hold for every possible Q. Say it has to hold for a couple of Q's that you sample. All right, and now lastly, we have this subproblem here that this minimum over this is less than or equal to gamma for each one of these, and now we just add those constraints into the main problem. All right, so this has to be less than or equal to gamma. So for each Q, right, each Q gets its own V that minimizes this. All right, so you get, and let's note here, so this is V transpose X transpose V, and then this one can be written as, we can square it and say V transpose V equals 1 for each one of these. Right, and now this is a polynomial optimization problem, and we can just sample, as many as we can deal with to try to approximate the original problem, and then apply sum of squares to this. All right, and now notice each one of these is just a real number. Right, so now the number of constraints is 3p, not m plus n squared plus mn. All right, so lastly, putting this all together, and this is actually for the original problem, the controls problem. So it's the problem we've been talking about with an extra layer of complexity with these binary variables. But that's one nice thing about using a polynomial is the binary you can just throw right in there, right? So okay, so we have this. It was a small enough problem that we could grid it up and solve it exactly. The green is the actual solution here. And the beta is a problem parameter, right? So you have a different problem for each value of beta, and it was something where we knew at 0, it went to 0, and bad things happen at 0. So we really want to see, how, if we were capturing that well. So this is the actual. This is the upper bound with the extra subgradient fine tuning. So that tracks really nicely. And now the red is the lower bound when you only sample 2. So this should be P up here. But so the red is the lower bound when you only sample 2 of these Qs. And the blue is when you sample 3 of them. All right, so it did pretty nicely around 0. It breaks off, but it was better than I would have expected for only taking 3 out of this big space. All right, I'm pretty much out of time, so I'll jump to this future. So I'm interested to hear if this kind of problem has arisen for anyone else. It was a simply stated thing that arose naturally, and yet I haven't heard of it arising elsewhere yet. As I mentioned, it would be nice to get a more precise statement about this convex heuristic where you can see a certain pattern, but I haven't been able to formalize that in any real way. Lower bound, it would be nice to have something not using SOS, because the whole point is we want to be able to do this for very large systems. And possibly, if we could use our knowledge from the upper bound to instead of just randomly sampling for the lower bound, perhaps use that knowledge to more intelligently choose these queues. Perhaps that would let these lower bounds converge more quickly. Thank you very much.